Okay, so yesterday we were discussing the following theorem. So we have please check if the notations are the same. Okay, so fix intermediate law. So we have that U is in C2 below, and hence we have that we know the Poisson kernel. So we have that U of x is equal to 1 minus, r squared minus, r squared minus x squared divided. So let's do the proof. Okay, x minus y to the n. And here there is a constant, it should be, please check, sigma minus 1 rho. Is it correct? Constant? Well, boundary of below. Okay. For any, constants are correct? For any sigma in minus, no, the representation formula. Yes, okay. And here there is rho squared minus x squared. And then there is G. G, but G now, G is U. Okay? G is U. is equal to, now fix, right. Okay, so I just was repeating this is the statement of the Harnack inequality that we wrote yesterday, exactly the same, okay? And this is, I'm starting with the proof. So I fix an intermediate rho. I have small r and capital R, and there is rho. And then U is harmonic in the big ball, so it is surely very smooth up to the closure of the intermediate ball. Okay. And we have the representation formula that we saw yesterday, that surely U can be written as an integral of its boundary values multiplied by this kernel here and these factors. Okay. Now, suppose for the moment, so this is true for any x here. Now, suppose for the moment, suppose initially, so this is the big theorem that we saw yesterday. Existence, uniqueness, and representation formula for the solution on a ball. Okay. See yesterday, see that for me. Now, suppose initially that x is on the boundary of the ball. Okay, so this clearly is also equal to 1 minus, because we are integrating with respect to y, so rho squared minus x squared sigma minus 1 rho integral y minus y. Now I want to, so we have that x is here and y is instead on the boundary of the rho. So x minus y, so y minus x, say, is what? Is equal, sorry, when x is here and y is here, is equal to rho minus r less than x minus y. Okay, by the triangular inequality. So, therefore, 1 over x minus y is to the n is less than or equal to rho minus r to the n. Okay. So, from this formula here, we get that as soon as x is here, the boundary of the R, we have that u over using the fact that u is positive, is not negative. So, using this, we have the following upper bound. So we have rho squared minus r squared divided by sigma n minus 1 rho divided by 1 rho minus r to the n. Okay. And then we have the integral over the boundary of v rho u of y dh n minus 1. Okay. Maybe there is a simplification that we can do. So this is equal. So I have rho plus r divided by sigma minus 1 rho, and then there is 1 over rho minus r to the n minus 1. And then I have, okay, let me write it, integral of the boundary of the rho u of y dh n minus 1 y. And now we know that u is harmonic, right? So it's natural to write here, to divide by rho to the n minus 1 and multiply by rho to the n minus 1 in order to use the surface mean value form. No? So the idea is now rho plus r divided by sigma, no, by rho to the n, rho minus r to the n minus 1, rho and then we have 1 minus n minus 1. So I've rewritten this, and multiply and divide by rho to the n minus 1 u of y h n minus 1 y. Okay? Which is equal by the surface mean value formula is equal to, this is u of 0, no? So is equal to u of 0 multiplied by what? So we have rho to the n minus 2 rho plus r divided by so suppose n larger or equal than 3 again in this these complications. Rho minus r to the n minus 1. Okay? So this is equal to
cannot be equal to?
No, could be, of course, but I'm doing the computation supposing that. This is now this statement is general. So now let me write this as follows. Let's see what happens. I write rho 1 plus r over rho divided by rho to the n minus 1 1 minus r over rho minus 1. Okay. Huh? And so this is equal, so I can divide here, and we have 1 plus r over rho divided by 1 minus r over rho to the n minus 1 multiplied by u of 0.
Yeah.
So here there is u of 0 here, and here there is u of 0. So we have the upper bound by this constant. Okay. Here. So by the weak maximum principle, okay. Do you agree that by the weak maximum principle, this is for the moment has been obtained under this constraint here. So we have on the boundary of the ball, we have that u of x is always less than or equal than that constant, and therefore also inside by the weak maximum principle. Huh? Now this rho was arbitrary, smaller than small r, since rho was we obtain for any x and br. The other inequality is similar. Other inequality is a similar proof using the minimum principle. Okay, so this gives this important inequality. So as you can see, this constant here, so as I was saying, we have an immediate corollary of this. Then,
why we didn't choose directly like from the beginning R?
small r, because I was...
Why we need rho, I mean, we didn't choose big R.
Regarding to that also, I think maybe you should put BR bar.
Why?
It's the same, of course. Here it's clear it's the same by continuity. That's it.
And yes, I also have this question.
Because I would like to have, so I have to write an inequality in this ball, no?
Yeah, but I mean, why we need this rho? because in the proof we didn't.
Maybe we could directly take.
We can do.
No, we cannot directly take capital rho. Sorry, we cannot directly take small rho equal capital R. This not because I don't have any information on the boundary values, on the smoothness up to the boundary. So I am forced to fix an intermediate rho where there I am surely smooth up to the boundary. But just as, no? Just a small remark. Okay, so this is seems to be okay. It's an important, actually extremely important inequality. In particular, this kind of inequalities in elliptic. There are also parabolic versions of such inequalities. Are very important when studying regularity of solutions of of this kind of elliptic partial differential equations. So, okay. Yes, the corollary is that there exists a constant. Okay, there exists constant depending on the dimension such that sup another version of this inequality is the following: sup over bi of u less than or equal is another way to express the this inf of u. Okay, let me redo the proof. I think we saw yesterday. Okay. Let me just repeat very quickly. We have that u of x and u of y, so for any x and y in the ball, these are bounded above and below by 1 plus r divided by 1 minus r u of 0 larger equal than 1 minus r. And therefore u of y, for instance, you can now you have, I mean, you have a point on which you can use to couple the two to make a chain of inequalities. So u of y is less than or equal than 1 plus r over r 1 minus y over r n minus 1 u of 0 is, by the way, smaller or equal than this constant to the minus 1 multiplied by u of x. So we can write an inequality between the oscillation between u of x and u of y. So this is 1 plus r to r minus 1 r to the r. And so you find this constant equal. So for any x, for any y, we have that for this constant here, which is we have this inequality, therefore passing to the supremum over y, supremum of y br of u of y is less than or equal than c n r u of x for any x in dr, and therefore now passing to the infimum with respect to x. This now is a number. Same constant. Infimum. Which is this inequality. Okay. Fine, so let me tell you an interesting result. Corollary, ma maybe più. So let U be harmonic in Rn. Harmonic. Let's see if we are able to prove together this harmonic in Rn. Bounded below. Because you recall this theorem in complex analysis for entire bounded homomorphic functions. Okay. This is a sort of very similar result in any dimension. Let's see if we are able to prove it. So, yeah, the statement is let U be harmonic in a Rn bounded below, then U is constant. Can you see the proof? Of course, it's an application of proof. We have to use an inequality.
What the infimum is constant.
Yeah.
So the supremum also is bounded.
Let's see how to use it clearly. So Harnack inequality has a first assumption, which is important. Must be not negative. Okay. So here it is not written, it is negative. So what do we do?
Take the difference with
U minus some.
Yes, because we know bounded below means U bounded below means there is some constant such that U of x larger or equal than m for any x in a line. Okay? Exactly. So why don't we take V equal U minus m. Now this is harmonic and this is non-negative. Harmonic in Rn and V is larger or equal than 0. So we want to apply Harnack to V. In other words, we can reduce ourselves to suppose that U is larger or equal than 0. Okay? Now we can apply Harnack to V. In other words,
corollary of the theorem?
Corollary.
I think that we can use the theorem. So fix R positive. So, and what do we know? We know that for any from Arnac inequality, for any R larger than R, we have u of x, so u of x less than or equal than 1 plus over R. I think that now you imagine the proof, but let me write it in any case.
You take the lead of operators.
Yes. This is true for any capital R and for any x in the R. Okay. We have so now what is natural to do is to let capital R to plus infinity, because the domain of our function is the whole space, so we can do this. Letting R to plus infinity gives, this is 1, so gives u of 0 less than or equal to u of x less than or equal to u of 0 for any x in the R. Which means that u of x is constantly equal to u 0 in the R, but this is true for any R. Okay, they are more or less equivalent. Okay, so this is a very nice global result on harmonic functions. Now, yes, now there is another version of Arnac inequality that is valid on more general domains. So let me write it. So here. So let omega be open, connected, bounded, say. Then for any open omega for any open omega prime, the closure of which, remember that this means simply this. And for any open omega prime strictly contained in omega, there exists a constant depending on n omega prime and omega, such that of u, sorry, let u, okay. Let u larger or equal than 0 be harmonic omega. Then for any open omega prime, less than or equal C omega. Can you see? So can you see the proof of this? It's not easy. Yeah? This is not completely immediate follow from. So I think that the idea is the following. So you have omega. Then you have omega prime. And the idea is this, and then you have to take 2 points, x and y, in omega prime, and then start to compare ux and uy, as before. No? So I have 2 points here. Start to compare ux with uy. And you know how to compare when you are in balls.
You need balls.
You need balls. You need a chain of balls connecting. Essentially, you need a chain of balls somehow connecting the 2 points. Okay. So the 2 points. Let's see which kind of balls are we going to use. Two points. So we choose finite family. Of balls B are xi, B are xi, with I from 1 to some index that I k, 0k, 0 to k, so we choose k in n, and the finite family of finite family of ball BRI xi from any I from 0 to k with the following property, such that here we have to be okay. So xi belongs to omega prime for any I from 0 to k. The union, so B Ri xi is contained in omega for any I from 0 to k. The union So I need to, actually I need two radii, not only one radius. So I need to take I will be, say, I need to take two radii. So union from 1, 0 to k b r I, say, divided by 4 contains omega prime. So I take the centers are inside the smaller omega prime. All bolts are inside the big omega. The union cover, because this is compact, the closure of this is compact. 1, 2, 3, and then maybe another condition. So for any I from 0 to k maybe k minus 1, there exists j from 0 to k such that xi plus 1 belongs to b rj over 4 xj. xi plus 1 points xi plus 1 for any I brj xj. So in this means that the distance between the centers should be bounded by rj over 4. Okay. And yes, this seems to be. So please check at home if all these conditions can be fulfilled. So once we have this, what do we do? Now we fix x and y. Now fix x, y in omega prime. And we start to consider, so x belongs to some, they are in omega prime, so they are inside some of these bolts. Okay, x, say, belongs to one of those. Let me call it, the index is I, 4, and y belongs to be some of these, same. Let me call this index BL. With I and L from 1 to k. For some, there exist I and L in 0, k, such that. Okay. So, and now we start to write the connection. So we do x. So suppose that L is larger than I. Suppose that L is larger or equal than I. Okay. Otherwise, there is an easy modification. So suppose we can assume. We can assume L larger or equal than I. And now we start to do a chain of centers. So consider x, xi plus 1. Etc. xl minus 1, xl, y. So we consider these points. And to any of these, to any pair, I mean, we can use the Harnack inequality on bolts. Okay. So let's see how. apply ux. There is a constant now. The constant we have, say, we are taking R is Ri over 4 and capital R is Ri. Okay? So our famous constant now is 1 plus R over R divided by 1 minus R over R to the n. No? The constant which compares ux and uy. You remember is a corollary, one of the corollaries. So this is what now? Is 1 plus Ri over 4 divided by Ri, so we have 1 over 4 divided by 1 minus 1 over 4 to the n. To the n. Okay, and this constant now is a constant depending on the dimension. Okay. So now we start to bound ux less than or equal, because we are in the ball connecting x and xi. So we have that u of x. So let me call this constant Cn. Yes, it's a constant depending on now. So now we work here. There are 2 points in the same ball. This ball is of some radius, but they are both in the same ball. So there we can apply Dirac in that ball. Okay, so now we find Cn u of xi. Now we go on, because the constant is always that, it's independent of the index now, just a constant depending on the dimension. And so now we go on, and this gives us u of xi plus 1, and then we go on up to y, and I think that more or less probably is the difference between the indices, and then is plus 2, no? Because there is this x and this y which are outside the family of indices. So I do L minus 1 plus 2 steps. No? Each time I do a step, I gain a power of the same constant. No? How many steps I'm doing? It should be L minus I plus 2, and this 2 is due to the first and the last, because these are not numbered by indices, just 2 points. U of y. Now, this concludes, because these indices, I mean, these are numbers depending only this is a constant depending on the dimension. L and I now depend on omega prime and omega, there is just in the geometry of omega prime. U. Okay. Let's see another consequence of probably also this you have already seen, but Let me tell you another consequence of this kind of clever inequalities. So, okay, for all, maybe monotone sequences of harmonic functions. Harmonic functions. So suppose that you have sequence. So of harmonic functions. Omega. Take a point. Suppose that it is tonic, so UH less than or equal than UH plus 1 UH. Suppose that there is one point such that exists, say, the limit finite. Just this. Now take omega be open bounded. Only this point. You have only just one point.
Yeah, I mean results.
Ah, the result, see. Ah, yes, yes. Then UH converges to. There exists an harmonic function U. In omega. Such that uniformly so fix, take, say, omega prime in this. Take two indices K and H and N. K say larger than H. And consider U K minus UH, which since k is larger than h, this actually is also uk minus uh, because this sequence is increasing. And then consider the supremum of this in omega prime. Supremum of this difference. So this is equal of this difference. Now we are, and of course uk minus uh is harmonic. This is harmonic. In omega. So we are in a position to apply the previous version, the last version of Harnack inequality in omega and omega prime. No? So by the previous theorem, there exists a constant. Suppose also that omega prime contains x naught, which is not restrictive. So so we have to add here to omega prime, and suppose also that x naught belongs to omega prime. Take k and l, k and h larger than. We consider sup. So by the previous theorem, Harnack theorem, there is a constant, positive constant, such that sup uk minus uh is less than or equal to the constant times the infimum uk minus But now, since we are taking x0 in omega prime, this infimum is less than or equal to the value at x naught. Okay. So this was omega. UK x naught. Now we have to use our assumption. No? Okay, so now we have to use an assumption. So there exists, by our assumption, there exists an index such that, so this is going to 0, no? So this, there exists an index, so for any epsilon positive, say, exists an index such that for any k and h larger than this. This is less than epsilon. No? Therefore, this sup less than some new epsilon, and epsilon multiplied by this constant, some epsilon, constant time epsilon. So our sequence UH actually is uniformly Cauchy, is a Cauchy sequence. Uniformly. So what does it mean? It means that it converges uniformly on omega prime to something, and this something by our theorem must be harmonic. So I don't know how it's called by Cauchy principle, by theorem, by Cauchy. By Cauchy convergence theorem, theorem on Cauchy. Hence, by Cauchy, by Cauchy principle, say. I don't know if it is Cauchy. UH exists U harmonic in omega prime such that UH converges to U in uniformly. There exists U harmonic, I mean, not only Cauchy principle and our results and what we know about closure property. I mean, there is a uniform limit on omega of this, but we know that if a sequence is converging uniformly, then of harmonic functions, that this limit is not only continuous but is also harmonic. So I have not written here, but and what we know about harmonic functions, what we know about uniform limits, let's say, about uniform limits of harmonic functions. There exists an harmonic function in omega prime such that UH converges to U uniformly in omega prime, which is almost what we want. Huh? And now I think it's not difficult to conclude. It's not difficult to conclude because it's sufficient to invade omega. Now we take, say, the sequence. Now take, say, the sequence omega n of open sets. Say x naught and proceed. So I leave you. So if x is in omega n, you have this u, but this u you can find the new, the same u for any. It's easy to find that you can extend u from omega n to omega n plus 1, omega n plus 2, and then at the end an harmonic function in the whole of omega, the same u, always the same u. Okay, so this is also interesting. Finally, the last result, it's also very, very interesting. I would like to tell you. Following theorem. Well, you know that if you have an holomorphic function, say in dimensions, an holomorphic, in one complex variable, if you have an holomorphic function which is holomorphic in, say, in a ball, in a disk, without a point, no? If it is bounded, you know this result that you can be removable singularity result. Yes, you can remove a singularity if you have an holomorphic function in a disk, minus 1 point. So you know it is holomorphic in a disk up to 1 point. And you also know that this holomorphic function is bounded. Then there is another holomorphic function which on the whole disk with the point coinciding with the previous one outside the point. Did you see this?
Yes.
How is it called? Is a well-known resulting complex, I don't know, removable singularities maybe? No?
I'm not sure
I
it has
don't
a
remember the name.
I'm not sure it has a name.
We know that there are different kinds of singularities. Removable.
Exactly.
It is not removable.
So it cannot be bounded. Yes, also, but the function cannot be bounded in a neighborhood of the singularity. And then there are these Picard theorem that says that that it may happen. The singularity can be so bad that the image fills the wall of C or C minus 1 point. That is not singularity.
The image is very small.
Yes, also. So theorem. So let U be harmonic in a ball in the R, say, minus the origin. And now we have to write the analog assumption of being bounded in any dimension. The analog assumption is interesting. So be harmonic in Br minus 1 point, and suppose that limit U of x is 0. So this kind of assumption means, look at the first one. The first one can be written as 1 over x to the n minus 2. similarly this. So our assumption essentially means that u of x divided by what we call the fundamental solution of the Laplacian. I think it was g, maybe g of 0 or g. Huh? Then the singularity. So this in principle says that, so since this goes to 0, you see, this in principle could also goes to infinity, could be unbounded as x goes to 0, but unbounded of the form that this times this must tend to 0. Then the singularity is removable. What does it mean? This means that there exists a function that I denoted by v, no, u hat. Okay. Then there exists u hat harmonic in Br, such that u hat is equal to u Br minus 0. Okay. Usually, I mean, the fact that the domain is a ball is not important. We could write apparently more, but it's the same, apparently more general result. So we could take u be harmonic in omega and suppose that 0 is inside omega. Okay. So in omega minus 0, and of 0 belongs to omega. Okay, and then doesn't change anything. This is the theorem, removable singularities. So the proof, we do the proof again. Suppose in this case, so you should do this maybe in 2 dimensions by yourself. Okay. Now we take a point x naught. So I think that the idea is the first idea is that take a radius, let me denote it by r, maybe. Then there is the omega here somewhere. And then I could consider the function u hat, which is nothing but, so I can consider the solution to minus Laplace of u hat equals 0 in Br, and u hat equal u in the value Br. Okay. So if I show, now, so the idea is that I take this boundary here. Here my function u has a trace, because u is very smooth, I mean this particular is continuous, and then I can uniquely solve the problem, the Dirichlet problem, no? Inside the disk with this boundary condition, no? And let me call this by u hat, maybe u hat. Actually,
You want the boundaries defined by continuity?
no, u hat, the boundary is defined by u.
Okay.
No?
So this close.
So u, because u is defined everywhere up to this point, no? And is harmonic, so it's infinity up to this point. In particular, u here is, say, continuous. So we have a theorem that says that we can always extend u in an harmonic way uniquely. So be the solution, be the unique, say, solution to this problem. This is given by the formula that we know. There is a formula for this, no? The Poisson kernel, etc. So now the idea is to show that actually u hat is equal to u. So it is sufficient to show. It is sufficient. So the idea is simply to replace u by this. It's sufficient to show that u hat is equal to u inside in the ball minus the. Maybe u hat is not a good symbol. Sorry. So I'm sorry for this. So let me call this v. Because then I have to. And then once I have proven that v is equal to u, then I can define u hat, u and v. Yeah. Okay. No? So, fix x naught here. We have to show that Vx naught is equal to Ux naught. Okay? There's not so much time, but maybe I can leave you this partly as an exercise indicating, so we have to show this. And now maybe I can indicate the steps so that you can try to do the steps by yourself. Okay, so take the difference now, W, V minus U, okay, and consider Z equal W plus fix epsilon positive. Take the difference and then consider this plus epsilon to the x to the 2 minus 1. So I am adding something harmonic out of, this is harmonic, out of the origin. Positive also. W is also harmonic out of the origin. Okay? So the steps and the proof is the following. So for you, home, okay, check that z is larger than 0, which is very easy, by the way, on boundary of BR. Why this should be so? Well, it's immediate, no? Because they are equal on the boundary. Therefore, this is 0 on the boundary and this is positive. So now show that it is, and this is the clever idea. So we have here this object is harmonic and is also positive. Okay, and then there is a singularity, that is a problem, but maybe we are able to find an annulus. An annulus. So we avoid the singularity, an annulus. So let me call this rho, such that also on this boundary here, this function z is larger or equal than 0. Show that there exists a rho sufficiently small but positive, such that two conditions, x naught is in the annulus, because x naught has been fixed. So the situation was fix x naught. I have erased, sorry, I have fixed x naught out of the origin, so somewhere here. Okay, now define w like there. W is and z like, so z is positive here, x naught has been fixed. Try to show that you can take rho sufficiently small such that, first of all, x naught is in the annulus. Belongs to BR minus B rho. No? And also z is larger or equal than 0 on boundary of BR. Rho, sorry. Excuse me. Rho. Yes. The idea for doing this is as follows. You can write z of x, this is equal to this minus this, v of x minus u of x plus epsilon x to the 2 minus n. Okay, so I can write this. So the idea for doing this this computation is the following. So you just do this vx times x n minus 2 minus ux x to the n minus 2 plus x. And now you see that so one of the two objects, I think it was V, maybe. V was smooth. No?
V is the solution.
V is smooth. So as soon as x goes to 0, this product goes to 0. This product goes to 0 by assumption. So as soon as modulus of x is sufficiently small, this is positive epsilon, and this is positive. So you can take a small radius, rho, sufficiently small, so that this z of x is larger or equal than 0 on the wall, and also you can avoid x0. You can, no? This is the idea. So I think you can do this easily, no? And now what do you conclude? You know that you have a domain and an open set, which is an annulus. And on this domain, you know that on the boundary, z is larger or equal than 0. So, by the weak, maybe minimum principle in this case, whatever, we know that z is larger or equal than 0 also inside. In particular, z is larger or equal than 0 at x naught. But epsilon is arbitrary. So we deduce that Vx naught minus Ux naught is larger or equal than 0. Is this clear?
Yes.
Let me repeat it once more. Eh?
Yes.
So we have found an harmonic function out of the origin which is positive on this boundary. Of course, this has a singularity at the origin, but now it is possible to show, thanks to our assumption, that there is a small rho such that in this annulus, the boundary of this small circle, that z is also positive. And also I can choose rho so small that x naught is out of the small, this bubble is here. Because x naught was different from the origin at the beginning, from the beginning. Yeah? So it has some positive distance, so we can reduce it. So we have an harmonic function now in the annulus. Z is harmonic in the annulus. In the annulus there are no singularities. Harmonic larger or equal than 0 on the boundary of the domain, omega is the annulus. Therefore it must be also larger or equal than 0 inside the annulus. In particular at x naught, because x naught is inside the annulus. So z of x naught, which is this object, is larger or equal than 0. And then you let epsilon to 0, and so you get that this is larger than or equal than this at x naught. And then you exchange v into w into minus w to get the opposite inequality. It's not so easy. It requires, but these are the steps. Once you get the opposite inequality, it means that you have proven this. And this concludes the proof. This is difficult, but okay. I hope that were you able to take the ideas on this?